Greetings of the day and a very good morning. I welcome you all to last lecture of module number 3. In this module, we have been discussing over last 4 lectures about series compensation or voltage compensation, and we have discussed the use of dynamic voltage restorer custom power device, that is DVR, as a voltage compensator. We have seen how we can synthesize the filter or compensation voltages using DVR as a voltage source inverter for compensation of voltage unbalance, for compensation of voltage drops, and also for compensation of voltage harmonics. Our theory was supplemented by phasor diagrams and also by solution of a few numerical problems. To end our studies on dynamic voltage restorer DVR as a series custom power device or as a voltage compensator or series compensator, let me again discuss the phasor diagrams with you for 3 different conditions. Number 1, voltage sag. Number 2, voltage swell. And number 3, voltage unbalanced voltage sag. Okay, although we have already discussed these phasor diagrams, I will redraw these phasor diagrams but with a slightly different pattern. So we will go for, let me write here, phasor analysis. Okay, I will take first case A, voltage sag. Let us suppose there is dip in the voltage. There is a momentary dip or momentary sag in the voltage. In that case, what will your DVR do? It will inject a compensation voltage in series with the load bus or load bus voltage, and it will try to maintain load bus voltage constant even in presence of voltage sag. So phasor diagram will look like this. This is our circular trajectory, and I will write here, this is the trajectory of source voltage Vs. Okay, and we wish our load voltage should remain equal to source voltage. Let us suppose this is our pre-sag voltage. This is V pre-sag. Pre-sag means, of course, it is VL load voltage. Pre-sag means that voltage sag has not yet occurred. There is no voltage sag. There is no dip. So in this case, this pre-sag voltage is exactly equal to, say, source voltage. It is equal to source voltage, right? Now what happens, and let us suppose this is the current, load current I. It is lagging behind the voltage by a phase angle phi L. Right? Now let us suppose that a sag, momentary dip in the voltage has occurred, momentary sag in the voltage has occurred. And when momentary sag in voltage occurs, this is our diagram, schematic diagram. This is source voltage phasor. This is source or feeder impedance. This is current I. This is voltage at point of common coupling, PCC, which is also called terminal voltage. I have not yet connected my DVR. This is my load. So in absence of DVR, my load voltage is equal to pre-sag voltage Vs. But when I connect my DVR here, okay, DVR will inject compensation voltage only when there is a dip or there is a variation or change in the voltage. Right now there is no change in the voltage. Let us suppose at time t, a momentary dip or momentary sag in the voltage has occurred. As soon as voltage sag occurs, what happens? This terminal voltage decreases and your this DVR injects a compensation voltage Vf in series with the load voltage to maintain load bus voltage equal to source voltage even in presence of voltage sag. If you remember, when DVR acts, it injects compensation voltage, the phase angles of all voltages change. The phase angle of this Vt changes. The phase angle of Vt, I mean without DVR injection, the Vt is equal to V, I mean before sag, before voltage sag has occurred, your Vt is equal to VL. And whatever is the phase angle of load voltage, same will be the phase angle of terminal voltage or voltage at point of common coupling. But as soon as voltage sag occurs, so Vt dips and your DVR immediately injects a compensation voltage Vf to make VL, to compensate for this dip in the voltage. And then what will be your load voltage? It will be Vt plus Vf. And therefore, this injected voltage Vf is probably at 90 degrees with respect to this current. So that will change the phase angle of this terminal voltage. So therefore, what will happen to terminal voltage? If this is your terminal voltage, Vt, its phase angle will change with respect to, the phase angle of terminal voltage will not be same as phase angle of load voltage. It will be same before sag, but during sag, when compensator is injecting the voltage, its phase angle will change. Now this is your terminal voltage. Terminal voltage has dipped because of voltage sag. Okay, if DVR is not there, then load voltage will also dip. It will be same as Vt. But in presence of DVR, what DVR will do? It will inject a compensation voltage. This is the compensation voltage Vf injected by your DVR. So it will inject the compensation voltage in such a way that this load voltage is maintained constant. This becomes your load voltage during sag. So it brings load voltage back to original value, but of course with a different phase angle. You have solved a couple of numerical problems for operation of DVR, and you have there seen that when DVR acts and it regulates the load voltage phase angle changes. Okay, and when this is the load voltage, what will be the load current? Load current will be this. Let us call this I dash, and it will have same phase angle as before the sag. Because the load impedance remains the same, load impedance has not changed, so load phase angle will remain same, phi L. Okay, so this is the injection voltage here. Okay, so so this is how voltage sag is taken care of by our DVR. DVR immediately injects this voltage Vf, and it brings VL back to pre-sag value. This is its pre-sag value, and this is voltage during the sag. It's brought very quickly brought because of injection of this compensation voltage. It is brought back to its original value. This is the same waveform which we have, same phasor diagram which we have discussed in last couple of lectures, 2 or 3 lectures. But there we had taken we were showing source voltage also. But here we are not showing source voltage, we are showing this load voltage with respect to terminal voltage at the point of common coupling. Okay, rest it is the same. Okay, so this is the phasor diagram during voltage sag. What about voltage swell? Let us suppose voltage swell phasor diagram we have not discussed there also in the previous lecture also. I will take case B, voltage swell. Let us see what will be the nature of phasor diagram during voltage swell. Again, this is my circular trajectory, and this is my pre-sag value of load voltage. This is VL pre-sag. Before, I should not say pre-sag, I should say pre-swell. This is the voltage before swell. Now I'm considering swell, not sag. This is load voltage, right? And let us suppose load current, this is load current I, phi L. You can show it lagging or you can show it leading, no problem. I am showing now leading, but you can draw the phasor diagram for lagging load current also. There is no such problem. Let us assume that there is an increase in the source voltage. What causes increase in the source voltage or swell? What are the causes of swell? Voltage swell. I have already discussed you in one of the earlier lectures. There may be different causes of voltage swell, like capacitor bank switching. Capacitor bank may be switched, sudden dropping of load. A large load has been suddenly cut off, so that will momentarily cause voltage swell. Or single line to ground fault on one phase, which causes voltage swell on the other phases, healthy phases. Okay, and there may be some other causes also. So as soon as this voltage swell takes place, Vt increases. In absence of your compensator, your VL will also increase. VL will be same as Vt. But in presence of compensator, DVR, what happens? As soon as Vt, common coupling voltage, Vt or terminal voltage increases because of voltage swell, Vf immediately injects a voltage which cancels the increase in the voltage and brings load voltage back to its pre-swell value. Okay, let us assume this is the voltage Vt during this swell. This is Vt, terminal voltage, and you can see it is greater than VL, or it is greater than Vs also, because this VL pre-sag is equal to Vs. It is greater. So it is because of swell in the voltage. There has been swell in the voltage. Now what will your compensator or DVR do? It will inject a voltage in such a way that it will bring this voltage back to its pre-sag value. So what it will do? It will inject a voltage like this. It will inject this much of voltage. This is the injected voltage by your DVR. When it injects the voltage, this becomes your load voltage now, VL, during swell. So you can see VL is brought back to or pre-swell value. Okay, because this is the circular trajectory. On this circular trajectory, voltages are constant. So it brings voltage back to its original value. And therefore, current phase angle will also change. This will be new current I dash with phase angle same as phi L. Okay, so this is the phasor diagram during swell. There has been swell in the voltage, and that increased the terminal voltage or voltage at point of common coupling, and your DVR immediately acted. It injected a voltage in such a way that it brought load voltage back to pre-swell value. So VL again becomes equal to Vs. Okay, so this is phasor diagram during voltage swell. Now third problem may be there, that there may be voltage sag on the three phases, but unbalanced voltage sag. Unbalanced voltage sag. Maybe on one phase there is 5% sag on phase A, for example. On phase B there is a sag of 10%, and on phase C there is a sag of 12 or 13%. So different sags on different phases. So in that case also your DVR should work perfectly. I mean, it should compensate all the three phase voltages, or sag in all the three phase voltages, and it should keep the low voltage across the three phase load constant, balanced. Let us suppose this is the sag in three phases. This is voltage VLA, phase A voltage. This is voltage VLB, phase B voltage. And this is voltage VLC. You can see the three phases have three voltages. This is, let us suppose there is no sag in phase A. Load voltage in phase A is same, but there is a sag in phase B voltage, and there is a one type of sag in phase B voltage and a different type of sag in phase C voltage. Okay, so you can see these voltages, the lengths of these vectors are different. So that means different voltage sags in the two phases. Because of this, what will happen to the terminal voltages? Your compensator should inject three different voltages in the three phases in such a way to make the three load voltages or line-to-line voltages constant. That means if this is your line-to-line voltage, for example, VAB, This should be your line to line voltage VLAB. This should be your line to line voltage VLBC, and this should be your line to line voltage VLCA. The job of your compensator or DVR is to keep these line to line voltages constant. VLAB should be equal to VLBC, should be equal to VLCA. So therefore you cannot see the sag in the three line voltages. How will you do that? So actually what happens whenever there is sag in phase B voltage, its terminal voltage also, there is a decrease in the terminal voltage. For example, this is VTA, terminal voltage, and this is, for example, VTC, phase C terminal voltage, and BLA is equal to same as VTA, because we assume that there is no sag in phase A. There is sag in phase B voltage and phase C voltage of the load. As soon as there is a sag in phase B voltage, the terminal voltage drops. Obviously इसका phase angle भी change होगा, ये drop हो गई terminal voltage. So what will phase A compensator do in the phase A? It will immediately inject the compensation voltage VFA in such a way ये load line to line voltage VLAB constant रहती है. Similarly, as soon as there is a different type of sag in phase C voltage of the load, the compensator immediately injects voltage VFC, and the sum of the two voltages, so when the compensator acts, it injects different voltages in different phases. So you can see line voltages remain constant. The length of this line to line voltage VLAB is same as VLBC, same as VLCA. So this is how your DVR, three-phase DVR, will take care of unbalanced voltage sags. In a similar way, it can take care of unbalanced voltage swells. Right. Now to end my lecture, I will discuss injection techniques, or I should say voltage injection techniques, compensation voltage injection techniques. Compensation voltage injection techniques. So try to understand, this is my circular trajectory. This is the trajectory of Vs. Let us suppose this is our load voltage. Okay, and this is the current. This is the load current I at a phase angle phi L. Now, if this is your load voltage, let's call this load voltage as VL1, which is equal to VL, and which is say equal to Vs. It is pre-sag voltage. Pre-sag voltage. Pre-sag load voltage. Let us suppose a voltage dip has occurred. As soon as a voltage dip occurs, voltage sag occurs, let us suppose terminal voltage has gone down. Your terminal voltage has gone down. This is the terminal voltage. Again, you can see from here, this is source voltage, this is feeder impedance, this is current I, this is terminal voltage at the point of common coupling. This is your DVR in this single line diagram of three-phase DVR, three-phase system, and this is load voltage, and this is the load. As soon as the voltage dips, okay, let us suppose your DVR injects a voltage, but let us suppose it injects the voltage, like this. This is the injected voltage. Let us call this injected voltage as VF1. Okay, so this is your terminal voltage. The voltage injected by your DVR is this. It is VF1. Okay, it is VF1. It injects this voltage. And it maintains, when it injects voltage VF1, it maintains load voltage as constant. So your load voltage is VL1 and it is same as pre-sag value. Without DVR, the voltage has dipped, it has gone down to VT. But immediately your DVR injects voltage VF1. Now you can see this injected voltage is not in quadrature with current. I told you last time that it is better that the injected voltage should be at 90 degrees to current. That means if this is the current, this should be the injected voltage VF or VF1, so that the phase angle between the two is 90 degrees and your DVR injects the reactive power. But in this case, it is not. It is injecting, this is your current and this is current I and this is the injected voltage. The phase angle is, let us say, phi. It's not 90 degrees. So therefore your DVR will inject reactive power and some portion of active power also. If injection technique is this, if you inject a voltage VF1 in series with VT or in series with VL to regulate the load voltage, make load voltage equal to source voltage. This is one type of injection technique. In this injection technique, your DVR should be fitted with, this is your voltage source inverter, basically your DVR. It should have some energy storage, energy source, say, battery energy storage system at its DC bus, so that it can inject reactive power as well as active power. With capacitor, it cannot inject active power, it can inject only reactive power. But since this injection technique demands both injection of reactive power as well as active power, so this is it. Second injection technique may be this. Again, your terminal voltage has fallen. The second type of injection technique may be this. I mean, your DVR may inject voltage VF2, which is not like this, whose phase angle is like this. अब आपकी current ये है और DVR injected voltage ऐसे है, VF2. Again, it is not 90 degrees. And you can see your load voltage now becomes VL2, and this is same as pre-sag value VL. So this is second type of injection method. Third type of injection method is, it may inject a voltage VF3 and load voltage will be VL3 equal to VL again. And last type of injection method is that it will inject a voltage in quadrature with the current. अगर ये current है, इसके 90 degrees पे ये voltage inject करेगा. तो ये, that is this VF4. Sorry, not here. I should not write VF4 here. This is your VF4 injected voltage, और यहाँ VL4 equal to VL again है. So it maintains load voltage constant immediately. But you can see here, if this is the current, DVR current, this is the injection voltage VF4. Now you can see the injection voltage is in quadrature with the current, and in this case your DVR is injecting pure reactive power. So since it is injecting only reactive power, so it is suitable for capacitor supported DVR, a DVR where you have a capacitor, not energy source. Other three techniques of injection, the VF1, VF2, VF3, require an energy source, like maybe battery energy storage system at its DC bus. But this technique demands only injection of reactive power for compensation of the voltage. So this is suitable for capacitor supported DVR or self-supported DVR. So these are three different techniques, four different injection techniques, compensation voltage injection techniques. The advantage with this last technique is that it maintains the load voltage. It maintains the load voltage constant equal to VL as soon as sag occurs, and it needs to inject only the reactive power, not active power, so that you don't need energy source here. You need a simple capacitor here. But the problem or drawback with this technique is that the injection voltage is largest of all. I mean, the kVA or MVA rating of DVR is higher than all other techniques, slightly higher. Okay. Where is the rating of DVR smallest? It is smallest in this case. So this is about various types of injection techniques of a DVR. And with this, we come to a conclusion or end of dynamic voltage restorer. Its basic structure, operating principle, injection techniques, how it compensates for the voltage. We have understood that with the help of phasor diagrams. What is the maximum voltage compensation capacity of a DVR, and what is the maximum voltage it can up to which it can take your load voltage, and how we implement the compensation technique using DVR, using hysteresis band control. And in today's lecture, we have drawn phasor diagram. We have done some phasor analysis. We have drawn phasor diagram for for voltage sag condition, voltage swell condition, and unbalanced voltage sag. And finally, with the help of this phasor diagram, we have tried to understand different types of injection techniques. Okay, so with this, we come to end of our discussions on series compensation or voltage compensation using DVR. Now, in this module, we are left with the third type of custom power device, which is called Unified Power Quality Conditioner, UPQC. This is the third type of custom power device. It's called Unified Power Quality Conditioner, or compensator also sometimes. UPQC. Why do you need UPQC? Actually, in power systems, what happens, the power systems should ensure a rated and sinusoidal voltage and rated voltage and balanced voltage to critical loads or voltage sensitive loads. What are the various types of voltage sensitive loads? Your hospital equipment like ventilator, life support system, patient database, diagnostic machinery, that's in the hospitals. They are all sensitive to the voltages. Similarly, in industries, variable frequency induction motor drives, they are very sensitive to voltages. I mean, they operate satisfactorily only when voltage supplied to them is perfectly balanced and there are no voltage sags, no voltage swells, no voltage flickering, no harmonics in the voltage. Similarly, there are many other types of devices, voltage sensitive devices, which we call as sensitive devices or critical devices, and they demand a perfectly balanced three-phase voltage if they are three-phase loads, three-phase balanced voltage, rated voltage without any dips, without any swells, without any fluctuations, and also without harmonics. There may be harmonics in your source voltage or voltage at the point of common coupling, but the job of custom power devices is to ensure that these critical loads get perfectly sinusoidal, balanced, and rated value and harmonic free voltage so that they operate satisfactorily. In industries, there are voltage sensitive loads like variable frequency drives, which themselves are responsible for various types of power quality problems. For example, in a variable frequency induction motor drive or adjustable speed induction motor drive, the situation is like this. You have a phase controlled converter as a front end rectifier. It's called front end converter. This is three-phase AC. It converts AC into DC. There is a filter capacitor CDC और यह आपकी DC लिंक वोल्टेज VDC बन जाती है. और आगे आपका three-phase voltage source inverter होता है. It gives three-phase output. This is your three-phase induction motor. It gives variable voltage, variable frequency output AC supply to induction motor for speed control, for torque control. This is generally the case with industries like textile machinery, like food processing unit, semiconductor manufacturing unit, rug industry, rug factory, rug manufacturing factory, and many other industries. This is the situation. Now these are called variable frequency drives. Induction motor drives are simply variable frequency drives or adjustable speed drives, ASDs. Because speed of the machine you can very easily adjust by frequency control using three-phase voltage source inverter. And they are very sensitive to voltage. Suppose there is a voltage dip, a momentary voltage dip or voltage interruption or voltage swell or voltage fluctuation. will immediately, there is an under voltage tripping mechanism in this drive. It will immediately disconnect your induction motor from the source. And when your drive gets disconnected from the source, it trips, all the manufacturing process stops. And if you have used raw material, say in food processing industry or in semiconductor manufacturing industry, all that raw material gets wasted. Okay, and you have to throw that out, that raw material. You have to use new raw material and you have to restart your drive. And restarting the drive takes a lot of time. So you are losing working hours also, you are losing labor hours also. So there is lot of loss of revenue because of these voltage dips. And they are also very sensitive to harmonics. The voltage which is present, which is available to these from the source, it should be purely sinusoidal, okay, at rated frequency and rated voltage. But the front-end converter, which is a part of this adjustable speed drive or variable frequency drive, this is also itself responsible for voltage fluctuation. Voltage harmonics. Because this acts as a nonlinear load with delay angle control or alpha control. It draws harmonic rich currents from the source. The three source currents, ISA, ISB and ISC, they will not be sinusoidal. They will be distorted. They will be non-sinusoidal. We have seen already in power electronics simulation lab, we have simulated single phase converter circuits, and we have seen how firing angle control or delay angle control results in distortion in the currents. And as soon as there are distortion in the currents, they result in distortion in the voltage at point of common coupling, and this itself is your point of common coupling. And here your voltages VSA, VSB, VSC, they get distorted. So these critical loads like these variable frequency drives, they are sensitive to voltage harmonics and voltage sags and swells, but they themselves are also responsible for one type of problem, that is voltage harmonics. Okay, so now you have to supply pure sinusoidal three-phase voltages at rated value, without sag, without swell, without fluctuations, and these voltages should be balanced, perfectly balanced. Okay, how to do that? Now you may immediately say that we will use a DVR, right? Your DVR will work here. Use a DVR here, three-phase DVR. It will inject the compensation voltages and it will make the voltage available to this drive balanced, perfectly sinusoidal, and it will maintain that at rated value. Okay, but the problem is that this drive draws non-sinusoidal currents, and there are other loads also which get affected because of these non-sinusoidal currents. You have protected your load by connecting DVR like this, but what about other loads? This is not the only load here. There are other loads. I mean, this is the point of common coupling, and many other loads, maybe three-phase loads and single-phase loads, other loads I will write. You have connected a DVR, here, this is DVR, and you have protected your critical load, variable frequency drive, from these voltage related power quality problems. But what about the other loads? They still are getting, non-sinusoidal distorted voltages because of nonlinear current drawn by, because of distorted current drawn by this front-end converter of your drive. You have to protect other loads also. Okay. So in that case, what you have to do, you need, in addition to DVR, you have to connect D-STATCOM also. That means in addition to compensation of voltage related power quality problems, you have to provide compensation for current related power quality problems. That means you have to provide load compensation also. So therefore, when you connect three-phase D-STATCOM, okay, so this three-phase D-STATCOM will be connected across your load, and it will, it will compensate these harmonics, and maybe there are load unbalances. It will compensate load unbalance also, so that these currents, ISA, ISB, ISC, which are basically coming from here, ISA, ISB, ISC, they are purely sinusoidal. Okay, so when these currents are sinusoidal, your other loads are protected. They also get sinusoidal voltages. But what about dips? There may be voltage dips, voltage swells, voltage sags. You can protect your load, a particular load like this load, from those dips by connecting DVR. By connecting D-STATCOM, other loads you are protecting from current related power quality problems like unbalance, voltage unbalance, and like harmonics present in the voltages, because you are making these line currents purely sinusoidal by connecting D-STATCOM. So therefore, there are many situations where another thing is that now you may say that let me connect D-STATCOM only. When I am connecting D-STATCOM only, it takes care of unbalance of the load. Maybe there is load unbalance here, and it may take care of voltage, current harmonics also, right? So it will take care of all current related power quality problems, but there may be still voltage related power quality problems. For example, this VSA, VSB, VSC, ये ऊपर से ही पीछे से ही distorted हो. See, this is the downstream and this is the upstream. आपका जनरेटर यहाँ नहीं है, यहाँ डिस्ट्रीब्यूशन ट्रांसफार्मर है जो आपके लोड को सप्लाई कर रहा है. That distribution transformer is supplying other type of loads also. उसको upstream हम कहते हैं. And maybe these voltages which are available, source voltages, they are already distorted and unbalanced and unregulated because of voltage related power quality problems upstream, somewhere up in the network. Upstream problems may be there. So although your D-STATCOM will provide load balancing here, load compensation here, making source currents perfectly balanced and sinusoidal, but what about these voltage related power quality problems? These voltages may suffer from frequent dips, that sags or swells or flickers, and they may also be distorted, and they may be unbalanced also because of distortion, because of problems upstream in the upstream network. So to provide solution and protect your sensitive or critical load from those voltage related power quality problems, in addition to D-STATCOM, you have to connect DVR also. So therefore, for many critical loads such as industrial loads and other type of critical loads, you have to protect your loads from voltage related power quality problems as well as current related power quality problems. So in that case, you have to provide load compensation as well as series compensation also. So you have to connect both D-STATCOM as well as DVR. D-STATCOM will provide load compensation. It will provide solution to current related power quality problem, and DVR will provide series compensation or voltage compensation. It will provide solution to voltage related power quality problems. So in many critical loads such as large industrial loads, both have to be provided. Now the combination of series compensation and shunt compensation, or the combination of series compensator and shunt compensator, that becomes a new custom power device which is called Unified Power Quality Conditioner, UPQC. UPQC is actually a combination of shunt compensator and series compensator. It is schematically shown like this. This is, for example, your source voltage, and this is source impedance, which is equal to RS plus JXS, and this is current, source current IS. So what you will do, you will connect DVR here. This is VT, voltage at point of common coupling. ये आपका point of common coupling है. So it will inject compensation voltage VF. Okay. So ये आपका DVR है, which is basically a three-phase voltage source inverter. This is the single line diagram of three-phase distribution system. और इसका DC, इसकी DC बस ये है CDC प्लस माइनस VDC, DC बस वोल्टेज है. ओके. और आगे आपका अब लोड है. तो लोड को प्रोटेक्ट करने के लिए व्हाट यू डू, यू कनेक्ट D-STATCOM also, and this is D-STATCOM current, उसको हम फिल्टर करंट भी कहते हैं, IF कंपनसेशन करंट, और ये आपका D-STATCOM है. This is D-STATCOM like this. और DC बस ये शेयर करते हैं. You don't need separate DC bus for D STATCOM and separate DC bus for DVR. They have common DC link. I will write here common DC link or common DC bus. So this is your, और ये आपका लोड होगा, ये लोड वोल्टेज है VL and this is load current IL. ये आपका लोड है. This is the load. It may be 3-phase load, 3-phase 3-wire load, 3-phase 4-wire load, 3-phase balanced or unbalanced load, linear load or non-linear load, or it may be a combination of single phase and 3-phase loads. Okay, so therefore this is your DVR and this is your D STATCOM, and the combination of the two, in दोनों की combination ये है, it's called, it becomes your UPQC. The situation is that you have to provide solution to current related power quality problems. That is, you have to provide load compensation that you do with the help of D STATCOM, and simultaneously you have to protect your load from voltage related power quality problems also, like voltage sags, voltage swells, voltage flickers, voltage fluctuations, harmonics, voltage unbalance. That is taken care of by series compensator DVR. So DVR is series custom power device or series compensator, and D STATCOM is shunt compensator or shunt custom power device. And this DVR provides solution to voltage related power quality problems, and D STATCOM provides solution to all current related power quality problems, so that this load and other loads at the point of common coupling, they get 3-phase balanced, regulated and sinusoidal supply. This load as well as other loads which are connected at the point of common coupling. Okay, so this is UPQC, Unified Power Quality Conditioner. So therefore UPQC, you can see it is a combination of DVR and D STATCOM. Now this UPQC, here you can see I have connected D STATCOM shunt compensator on the right side and series compensator, that is DVR, on the left side. But if you see the literature, in the literature you have found that some researchers have connected D STATCOM on the right side and DVR on the left side. In that case, you get two types of UPQCs. You get, first of all, left shunt UPQC, like this. Let me show you the schematic diagram directly. I will show you the schematic diagram of that. That looks like this. This is Vs, source voltage, and this is your source impedance Zs, which is Rs plus Jxs. This Rs, Jxs, and this is source current Is. तो आप क्या करते हैं, ये शंट कंपनसेटर आप लेफ्ट साइड पे लगाते हैं. So this is shunt compensator. It is nothing but D STATCOM. और series compensator, that is DVR, आप यहाँ लगाते हैं. This is the compensation voltage VF and this is the compensation current, say IF. This is DVR. It's on the left side. और ये आपका critical load है. I will write here critical load. So this is the schematic diagram of left shunt UPQC. Why is it called left shunt UPQC? Because the shunt compensator D STATCOM is connected on the left side and DVR on the right side. That's why it's called left shunt UPQC. You have another configuration, another type of UPQC, that is called right shunt UPQC. Right shunt UPQC. So right shunt UPQC looks like this. This is again source voltage Vs, source current Is, and this is source impedance Zs, and you connect DVR here. This is the DVR injected voltage VF, this is DVR, and you connect D STATCOM on the right side. Shunt compensator you connect here. This is your D STATCOM. This is the compensation current IF और ये आपका critical load है. This is the critical load. So since shunt compensator is on the right side, that's why it's called right shunt UPQC. अब इन दोनों में which one do we generally prefer? If you search the literature, you go through the literature, research papers, research publications, you will find that right shunt UPQC is generally preferred over left shunt UPQC, because in right shunt UPQC the D statcom is just adjacent to the load, and it very effectively compensates the load for unbalance, for harmonics, and for other problems very effectively without requiring large rating of the D statcom. On the other hand, if your D statcom is on the right side, it will still compensate your load, but the rating of both DVR and D statcom will be higher. In right shunt UPQC, the ratings of the two converters, that's D statcom and DVR, will be less than that in this case. So therefore, right shunt UPQC is generally preferred over left shunt UPQC. Remember this. Okay. Let me now show you the complete circuit diagram or schematic diagram of three-phase UPQC. ये हमारा three-phase UPQC है. This is the source voltage, say VSA, source voltage VSB, and source voltage VSC. Three-phase voltages. Okay, and these are the line current, source currents ISA. This is ISB, and this is ISC. This is the source or supply neutral N. Then you connect the DVR here. ये आपका DVR है. Let me show DVR three-phase voltage source inverter. It's a three-phase voltage source inverter connected like this. Let me complete the circuit diagram first. Like this. I am connecting this is the common DC bus, CDC with DC bus voltage VDC, and this is your DVR, dynamic voltage restorer, series compensator. अब देखिए it is like this. Transformer reactance is represented by this LF, and it's connected like this, and ये connection आप नीचे लाएंगे. अभी मैं दिखाऊंगा how to connect it. उसके बाद आपका दूसरा फेज यहाँ से आएगा. It will come like this, और ये इस तरह connect होगा. And this is this and this, they are connected together. और आपका तीसरा यहाँ से इस तरह आएगा, third branch, और I should not extend it. यहाँ तक extend करने की जरूरत नहीं है. I can show it like this. This is DVR, primary winding, secondary winding, और इसका भी दूसरा टर्मिनल ऐसे connected है, and there is inductance LF in all the three lines. LF. So you have ripple filters across the transformer, injection transformer secondary. This is RF CF, ripple filter. Similarly, you have a ripple filter here, RF CF. Another ripple filter. I have explained you the operation of ripple filter. It converts PWM voltages into normal voltages, continuous voltages, RF CF. And this is the injected voltage, say VFA. This is the injected voltage, compensation voltage, VFB, and this is the compensation voltage, VFC. These are three compensation voltages. ठीक है. इसके बाद आपका डी स्टैटकॉम आगे आता है। डी स्टैटकॉम यहाँ से शुरू हो जाएगा, विच इज ऑल्सो ए वोल्टेज सोर्स इन 3-फेज वोल्टेज सोर्स इन्वर्टर। ये भी 3-फेज वोल्टेज सोर्स इन्वर्टर है, लाइक दिस। Let me complete the circuit diagram of voltage source inverter or D STATCOM first, and I will explain. DC bus common hai. Instead of showing this DC bus here, I can show it in the middle. This is the DC bus. This is DC bus capacitor, whose voltage is VDC and capacitance is CDC. Right? Now, these are the 3 lines, और यहाँ आपका लोड है 3-फेज critical load. This is critical load. It may be 3-phase load with load currents as ILA, ILB. These are the RMS values of load currents, ILC. Now what will this DVR do? This is your D STATCOM. Shunt compensator. It's the right shunt. It's connected towards the right side. ये ट्रांसफार्मर की लीकेज इंडक्टेंस यहाँ दिखाता है LF, ओके, एंड it is injecting the currents, like let us call this current as IFA, filter current IFA. Similarly, this is LF and this is filter current IFB with RMS value this, and this is transformer leakage reactance and this is filter current IFC. इसमें भी आपको रिपल फिल्टर्स लगाने हैं, 3 रिपल फिल्टर्स, RC, RF, CF, like this, star connected, Y connected like this. So this is ripple filter, because current will be pulsed in nature, PWM. To make that continuous current, the ripple filter is required. This ripple filter is connected to this line, this is connected to second line, and this is connected to third line. This is the ripple filter, right? So it is very much clearly shown here how, these are the dot conventions. So this is your UPQC, right shunt UPQC. तो ये आपका UPQC है, यहाँ से यहाँ तक, which is a combination of DVR and D STATCOM. This is UPQC. Of course, right shunt UPQC. Sometimes what happens, your load may be a combination of single phase and 3-phase loads. उसके लिए 3-phase 4-wire system है, वो मैं यहाँ पे ही दिखा सकता हूँ आपको. I can show you 3-phase 4-wire system like this. चौथी वायर भी आ रही है जो न्यूट्रल से आ रही है, मे बी लोड न्यूट्रल, और ये it injects the neutral current IN into the line. If it is 3-phase 3-wire system, then neutral wire is not there. If it is 3-phase 4-wire system, then there may be neutral current, heavy neutral current, because you are this may be a combination of 3-phase and single-phase non-linear loads. NLL means non-linear load. 3-phase non-linear load will not cause any current, distorted current in the any neutral current, because you already know this in case of a 3-phase system, those neutral, there's triple harmonic currents, third and triple harmonic currents, third, ninth, 50, these harmonics are not present in 3-phase systems. But if you are feeding single phase nonlinear loads also, like single phase AC to DC converter based power electronic loads, single phase AC to DC converter based loads, then those single phase loads draw these third and triplet harmonics also. And in one of the classes I have discussed with you, when single phase nonlinear loads are connected on a 3-phase system, 3-phase 4-wire system, because of these third and triplet harmonics, a very heavy neutral current flows, and that may cause neutral overheating and neutral burning. To avoid that neutral overheating or neutral burning, what is sometimes done, a 4th leg is also added to your D-STATCOM. ये चौथी leg है उसमें. And this neutral wire connection, ये जो neutral wire connection है, it is connected in the middle of this leg. And then you have to design your control algorithm in such a way कि इन दोनों की switching, इस leg की switching इस तरह हो जाए that this neutral current, which actually has to flow in the neutral wire, that is, this current is IN dash, it is equal to minus IN. This fourth leg injects a current minus IN, which is equal and opposite to the neutral current here. And what is this neutral current equal to? It is basically third and triplet harmonics. So this current will also be comprising of third and triplet harmonics, but it will be equal and opposite to this neutral current, so that these two currents cancel and no current flows in the neutral wire. There is no current in the neutral wire. Okay, so try to understand. This is very important. So this is the complete schematic diagram. If you want to show three-phase, three-wire system with only three-phase critical loads, and this is D-STATCOM, this is DVR, this is D-STATCOM, this is three-leg structure, this also will be three-leg structure. But if you have three-phase, four-wire system with three-phase and single-phase critical loads, three-phase critical loads and single-phase non-linear loads, then neutral current has also to be compensated. Then in that case, DVR will be three-leg voltage source inverter, but the D-STATCOM will be four-leg voltage source inverter. Fourth leg is connected to neutral, and it will, compensate the neutral current. It will make neutral current equal to 0. Now, depending upon the power rating, UPQCs may be of different types. Classification of UPQCs based on power rating. Based on power rating, your UPQCs may be of following types. Number 1, UPQCQ. Number 2, UPQCP. And number 3, UPQCS. These are the three types of UPQCs. I will explain them one by one. Let us consider UPQCQ first. Actually, it depends upon the injection techniques. This classification depends upon DVR, voltage injection technique. DVR में कौन सी voltage injection technique आप use करते हो? That will decide whether your UPQC is UPQCQ type or UPQCP type, or UPQCS type. Let me explain them one by one. Let us first of all take UPQCQ type. This type of UPQC. You will be able to understand it with the help of phasor diagram. Phasor diagram से आप इस तरह इसको understand करेंगे. ये as usual आपका circular trajectory है, which is the trajectory of constant load voltage or constant source voltage. And let us suppose this is your load voltage, VL, pre-sag voltage, pre-sag load voltage, which is equal to source voltage Vs. Now let us suppose there has been voltage sag. Okay, as soon as voltage sag comes, what happens? Okay, उससे पहले मैं आपको load current भी दिखाऊंगा. If this is load voltage, this will be load current IL with a phase angle phi L. What about source current? Source current कहाँ होगी? आपकी source current ये होगी. This will be your source current IS, which is also equal to IL. अब मैं source current दिखा रहा हूँ in phase with the voltage. I mean, it will be in phase with the source voltage. Source will see your load as a linear load, purely resistive load, and this source current will be in phase with the voltage. Why? Because you are not using only DVR, you are using D-STATCOM also. It is UPQC. What will D-STATCOM do? It will compensate for all the reactive power demand of the load. Whatever reactive power is required by the load, it will not allow that reactive power to come from the source, it will locally supply that reactive power, so that source से खाली active power आएगा, and therefore source current, although load current is at a phase angle of phi L with respect to voltage, with respect to source voltage or with respect to load voltage, but source current is in phase with the source voltage. Source current source voltage के phase में है. Why is source current in phase with source voltage? Because no reactive power is coming from the source. Who is supplying reactive power demand of the load? D statcom. अगर D statcom नहीं होता, खाली DVR होता, तो ये आपकी IS भी एक पर्टिकुलर फेज एंगल पे होती, वो इन फेज विद वोल्टेज नहीं होती. बट सिंस इन एडिशन टू DVR you have D statcom also, D statcom compensates for all reactive power demand of the load, so that only active power comes from the source, and source current is in phase with the voltage, source voltage, phase with the voltage. Okay. Now what will your DVR do? Let us suppose voltage sag has come. ये तो हो गया D statcom ने source current को in phase with source voltage बनाया, so that unity power factor operation results. Your source operates at unity power factor. That's okay. D statcom has done that job, and D statcom has, if there was unbalance also in the load, that unbalance is also compensated by D statcom. And if there were harmonics also in the load, I mean your load was non-linear, that harmonic compensation is also done by D statcom, so that the source current is in phase with the voltage during unity power factor operation, and the three-phase source or line currents are balanced and sinusoidal. That is done by D statcom. What will DVR do? Let us suppose a voltage sag has occurred. Okay, source side पे voltage sag आ गया because of some fault etc., or because of direct line starting of large induction motor, a momentary voltage sag has come. And as soon as voltage sag comes, what happens to your voltage at the terminal voltage at the point of common coupling? It falls. It becomes less than your load voltage. ये immediately fall हो जाती है. But what will your DVR do? अब आपके UPQC में DVR है, D statcom तो अपना काम कर रहा है. Now it is time for DVR to act. DVR क्या करेगा? Immediately injection voltage inject करेगा, compensation voltage VF inject करेगा. And when it injects compensation voltage, that will compensate for this voltage dip. यहाँ पे sag आ जाता है, right here voltage sag. It will compensate for this voltage sag, and you can see this is your injected voltage, and it will make this load voltage VL dash again equal to VL, again equal to VS. Source voltage के बराबर फिर से हो जाएगा. Okay, this is how it works. अब आपकी ये voltage जो है, ये voltage, this is your injected voltage, DVR injected voltage. You can see in this case, this injected voltage is at 90 degrees with respect to current. It's at exactly at 90 degrees. So your DVR is injecting a voltage which is at 90 degrees with respect to current. So what type of power it is injecting for voltage compensation? It is injecting reactive power, because voltage, DVR voltage is at 90 degrees with respect to current, so it requires to inject only reactive power. It does not require to inject active power. कोई active power इसको नहीं चाहिए inject करने के लिए for voltage compensation. There may be some small active power required for maintaining DC bus voltage constant, because in order to supply the inverter switching losses and transformer copper losses, that is very, very small. That may be 1 or 2% or even less than that. But for voltage compensation, it is injecting the reactive power. Since in this case, in this type of injection technique, UPQC supplies reactive power, purely reactive power for voltage compensation. That is why this type of UPQC is called UPQC-Q. Q stands for reactive power, because it supplies only reactive power. I hope it is clear. Now voltage sag, it very elegantly, addresses this voltage sag problem. Now let us see whether it can address voltage swell problem or not. Now let us suppose voltage swell has come. Assume करते हैं कि voltage sag नहीं आया, voltage swell आया. यह आपकी load voltage है, VL pre-swell, swell से पहले, which is equal to VS, right? और एज यूजुअल ये आपकी करंट है, लेट सपोज दिस इज लोड करंट आई एट अ फेज एंगल ऑफ फाई एल, ठीक है, राइट। And source current IS is in phase with the voltage because of D statcom. D statcom supplies all the reactive power of the load. So the current drawn by your load is in phase with the voltage Vs. यहाँ तक तो ठीक है. And let us suppose voltage swell has come. Voltage sag नहीं आया, अब swell आया. ये आपका swell यहाँ आया, इतना swell. I will write here swell, voltage swell. जिससे आपकी point of common coupling पे जो voltage है, terminal voltage, वो increase हो गई. This is VT. ठीक है. अब इस केस में आपका डीवीआर क्या करता है? डीवीआर इंजेक्ट्स ओनली रिएक्टिव पावर फॉर वोल्टेज कंपनसेशन. दैट मीन्स इट इंजेक्ट्स द वोल्टेज. ये अगर आपकी करंट है आई, इट इंजेक्ट्स द वोल्टेज वी एफ एट 90 डिग्रीज टू आई. तो यहाँ पे भी ये वही करेगा. सो इट विल इंजेक्ट सम वोल्टेज, दिस मच ऑफ वोल्टेज वी एफ विच इज एट 90 डिग्रीज टू द करंट. उससे क्या होगा? आपकी लोड वोल्टेज कितनी होगी? ये आपकी लोड वोल्टेज होगी. दिस इज योर वी एल डैश विच इज ग्रेटर देन वी एल, दैट इज ग्रेटर देन वी एस. ये आपकी. और अगर इसने नेगेटिव इंजेक्शन कर दी, दैट मीन्स वी एफ माइनस वी एफ इंजेक्ट कर दिया, तो उस केस में भी आपकी लोड वोल्टेज जो है वी एल डबल डैश, इट इज स्टिल ग्रेटर देन वी एल, ग्रेटर देन वी एस. सो यहाँ पे जो स्वेल आया था, सो दैट मीन्स इट फेल्स टू कंपनसेट फॉर दिस स्वेल. कंपनसेट करने के लिए इसको ऐसे वोल्टेज इंजेक्ट करनी है ताकि ये वोल्टेज जो इंक्रीज हो गई ये वापस सर्कुलर ट्रेजेक्टरी पे आ जाए. बट सिंस what type of injection technique you are using, your DVR is supplying injection voltage in quadrature with the current at 90 degree. It is supplying only reactive power क्योंकि इसके DC बस पे कैपेसिटर है, एनर्जी सोर्स नहीं है, बैटरी एनर्जी सोर्स नहीं है. सो इट विल सप्लाई reactive power only, and by supplying reactive power or by injecting the compensation voltages like this in quadrature with current, it will fail to compensate for voltage swell. तो आपकी वोल्टेज, लोड वोल्टेज या तो ये रहेगी विच इज ग्रेटर देन वी एस, या ये विच इज स्टिल ग्रेटर देन वी एस. सो देयरफॉर UPQC Q fails to compensate for voltage swell. Voltage sag, we have seen it elegantly compensates voltage sag, but it fails to compensate voltage swell. So there, that is why UPQC Q type is generally not preferred. अगर आपको पता है कि आपके सिस्टम में खाली सैग्स आएंगे, you are sure that swell कभी नहीं आएगा, then okay, this is one of the best UPQCs. But you never know when swell will come. Swell can come anytime. कैपेसिटर्स एनर्जाइजेशन की वजह से, ड्रॉपिंग ऑफ लोड की वजह से, सिंगल लाइन टू ग्राउंड फॉल्ट की वजह से, या दूसरे वजूहत, दूसरे रीजंस की वजह से. एनी टाइम वोल्टेज स्वेल कैन कम. सो देयरफॉर Q टाइप UPQC or UPQC Q will fail to compensate for voltage swell. Okay, that's why this type of UPQC is generally not used. And why is it called UPQC Q? Because it does the compensation by reactive power injection. It does not inject any active power. Okay, that's first type of UPQC. Second type of UPQC is UPQCP. Okay. I will explain the operation of UPQCP again with the help of phasor diagram. Again, this is your VL pre-sag voltage, which is equal to VS. Right? Now let us suppose voltage sag has come. Voltage, ये आपकी ये load current है IL, I, which is at phi L, and ये source current है. For example, let us suppose this is source current IS, which is in phase with the source voltage because of D statcom, unity power factor operation. Now sag has come. अब क्या हुआ है कि वोल्टेज सैग आ गया, यहाँ से यहाँ तक सैग आ गया. जो ये सैग आ गया, आपकी टर्मिनल वोल्टेज कम हो गई, so your load voltage will also drop, but your DVR part of UPQC will very quickly act and it will inject a voltage, it will inject a compensation voltage. आपका सैग जब आता है तो आपकी वोल्टेज VT it becomes less than VL pre-sag, yeah, it becomes less than VL. ठीक है, so what will your DVR do? It will inject a voltage VF in this direction which will cancel this voltage drop. So ये वोल्टेज है जो ये इंजेक्ट करेगा और आपकी वोल्टेज वापस VL पे आ जाएगी. So it will come back, it will touch the circular trajectory. So ये VL will be again equal to VS. अब आप यहाँ देख सकते हैं this injected voltage VF is in phase with the current. ये आपकी current है, this is current I and this is injected voltage VF. They are in phase. So therefore, since voltage of DVR is in phase with the current, so what type of power is it injecting? It is injecting active power. It's not injecting reactive power. Reactive power में voltage and current quadrature में होती है 90 degrees. Here voltage is in phase with the current. So it is compensating for voltage sag by injecting active power. So active power inject करने के लिए आपका DVR जो है इसको ये कैपेसिटर सपोर्टेड नहीं होना चाहिए. इट कैन नॉट बी कैपेसिटर सपोर्टेड. देयर शुड बी सम एनर्जी सोर्स. फॉर एग्जांपल BDC, बैटरी एनर्जी स्टोरेज सिस्टम शुड बी देयर. BESS, बैटरी एनर्जी स्टोरेज सिस्टम. A battery should be there which supplies this active power because capacitor cannot supply active power. So this DVR cannot be capacitor supported. It has to be battery energy storage system based, so that because the voltage compensation is done by injecting active power. It can inject active power only when it has an active power source on its DC bus, say something like battery energy storage system. So therefore it should have this battery energy storage system. So sag to ye compensate karta hai. Let us see whether it will be able to compensate swell or not. अब चलिए swell पे देखते हैं इसकी performance. As usual, this is your VL pre-swell, swell से पहले वाली voltage, which is equal to VS, source voltage के बराबर. ये लो as usual load current है I at a phase angle of phi L और ये आपकी source current है IS. अब यहाँ पे swell आ गया. Swell means आपकी voltage slightly बढ़ गई. ये swell आ गया. यहाँ से यहाँ तक I will call this swell, voltage swell. So that आपकी टर्मिनल वोल्टेज अब ग्रेटर देन VS हो जाती है और ग्रेटर देन VL हो जाती है और ग्रेटर देन VS. So what will your DVR do? DVR will immediately inject voltage, compensation voltage. वो opposite compensation voltage inject करेगा जिसका arrow इस direction में है. So this is VF. A negative injection voltage will be injected by DVR. Okay? जो इसमें वोल्टेज इंक्रीज हो रही है से 10%, ये भी 10% होगा, बट दिस विल बी इक्वल एंड अपोजिट टू दिस इंक्रीज इन द वोल्टेज. सो इस वोल्टेज इंक्रीज को कैंसिल करेगा और आपकी वोल्टेज वापस इस पे आ जाएगी. सो योर वोल्टेज विल बी बैक टू VL इक्वल टू VS. इस केस में भी आप देख सकते हैं दिस इंजेक्टेड वोल्टेज इज इन सीरीज विद द करंट. सो देयरफॉर अगेन इट हैज टू इंजेक्ट power, active power. In this case, of course, ये active power, it will draw active power from the source because voltage is negative, current is positive, so power is negative. Negative power का मतलब हुआ है instead of supplying active power, it will draw active power from the source. Okay, and no reactive power is involved here, and it will very elegantly address voltage swell problem. So अब इसको UPQC P क्यों कहते हैं? Because whether it is voltage compensation for voltage sag condition or voltage swell condition, in both the cases it does the voltage compensation by injecting active power or by absorbing active power. P stands for active power. That's why this type of UPQC is called UPQC P. इसका DVR की DC bus पे capacitors, it cannot be capacitor supported UPQC. It has to be energy supported or battery energy storage system supported UPQC, because it has to inject the active power for voltage compensation. Okay, and it very elegantly does the voltage compensation for both sag as well as swell. Whereas UPQCQ, you have seen, it can compensate for voltage sag, but it cannot compensate for voltage swell. But UPQCP compensates for both voltage sag as well as voltage swell. And the amount of power required to compensate is less. It is very less. You can see sag में भी बहुत कम voltage इसको inject करनी पड़ी और swell में भी बहुत कम voltage इसको inject करनी पड़ी. So therefore the rating of DVR will be very small. But the only problem is that you require a battery energy storage system at its DC bus. Okay, this is about UPQCP. Then last type of UPQC is UPQCS. I will write now UPQCS. We will again try to understand it with the help of phasor diagrams. Let us consider first voltage sag. So this is VL pre-sag. Sag se pehle load voltage, which is equal to Vs. Okay, and this is your load current IL, and source current is in phase with the voltage, so that unity power factor operation is resulted because of D statcom. अब इसमें voltage sag आ रहा है. Now there is a voltage sag. Let us suppose this much voltage drops. This is the sag, और आपकी terminal voltage less हो जाती है. VT is less than VL, that is less than VS. आपकी terminal voltage कम हो जाती है. अगर DVR act नहीं करेगा तो आपकी load voltage भी यहाँ आ जाएगी. It will drop. But DVR very quickly acts and it brings voltage back. अब इसमें इस केस में किस टाइप की इंजेक्शन करेगा? Let us suppose it injects this type of current, this type of voltage. This is the injection voltage VF. So therefore आपकी load voltage वापस pre-sag value पे आ जाती है. It's again equal to Vs. So therefore this injected voltage by DVR takes care of this voltage sag. And now in this case, if this is the current I, and voltage, injected voltage is VF. It is not at 90 degrees and it is not in phase also with I. It is neither at 90 degrees with respect to I nor in phase with I. It is at some different angle, say 110 degrees or something like that. I don't know. Maybe any value other than 90 degrees or other than 0. So you can resolve this into, in phase and out of phase component. That means now your DVR is, what type of power is it injecting for compensation of this voltage? It is injecting active power as well as reactive power, because this voltage you can resolve into two: VF in phase, VFR, and VFL, you can say. In phase component and out of phase component. In phase component is in phase with the voltage, so that means it is injecting active power. And out of phase component, quadrature component, is at 90 degrees with the voltage, so it is injecting reactive power. So by injecting active power as well as reactive power, it is doing voltage sag compensation. Okay, let us see voltage swell, performance on voltage swell. This is load voltage, which is equal to VL. This is VL pre-swell, swell se pehle voltage, which is equal to Vs. And as usual, this is load current IL at a phase angle phi L, or a load source current IS in phase with the source voltage for unity power factor operation, as done by UPQC, as done by this D statcom. So ये आपकी VL pre-swell, which is equal to Vs, right? अब swell आ गया तो आपकी वोल्टेज बढ़ गई. ये आपकी टर्मिनल वोल्टेज है VT. Now VT is greater than Vs, I mean it is greater than VL pre-swell. Pre-swell वैल्यू से ज्यादा है, right? तो ये आपका swell अब यहाँ आ गया, वोल्टेज swell. So DVR part of UPQC will very quickly act and it will inject a voltage. This is the injected voltage VF, so that load voltage comes back to its pre-swell value, and it is again equal to Vs. Now you can again see if this is the current, this is the voltage. Voltage is not in quadrature with current, and it is not in phase with current also. So you can resolve this voltage into two components, in phase component and quadrature component. That means by injecting this voltage Vf, the DVR part of Upqc is actually injecting both active as well as reactive power. In fact, in this case, it will be absorbing the power, but there will be both active as well as reactive power involved for voltage compensation. And it very elegantly does this swell compensation against voltage swell also. So therefore, whether it is compensation of voltage sag or compensation of voltage swell, in both the cases, it compensates the sag or swell by using or by injecting small amount of active power and small amount of reactive. Both active as well as reactive power is injected by it. And what is active power plus reactive power? That is called apparent power. So therefore, unlike Upqcq, it does not inject only reactive power. Unlike Upqcp, it does not inject only active power. It injects both active as well as reactive power, and that active and reactive power, that means that's called apparent power. That's why this type of Upqc is called Upqc's. It does the voltage compensation by apparent power injection. Okay. Now, when you have to compare the three types of Upqc on the basis of, power rating or on the basis of type of voltage compensation by DVR, we get these three: Upqcq, Upqcp, Upqc's. Upqcq is generally not preferred because although it does the voltage sag compensation, it fails to do voltage swell compensation. Now you have to make a choice between Upqcp and Upqc's. In Upqcp, the voltage sag and voltage swell compensation is done by injecting active power, and in Upqc's, the voltage sag and swell compensation is done by injecting apparent power. Which one will you? In both the cases, you need DC bus energy storage. क्योंकि इस केस में तो ये एक्टिव पावर कर ही रहा है इंजेक्ट, इस केस में भी रिएक्टिव पावर के अलावा एक्टिव पावर भी चाहिए. So you need battery energy storage system at the across the DC bus. If you have to make a choice between the two, I will go for this Upqc's, because if you see literature, research literature says that the power rating of the two voltage source inverters, D-STATCOM and DVR, is smallest in this type of Upqc's. इसमें तो एक्टिव पावर ये इंजेक्ट करता है और रिएक्टिव पावर जो ये आपका DVR इंजेक्ट करता है, इट शेयर्स दैट रिएक्टिव पावर विद D-STATCOM, क्योंकि आपका D-STATCOM भी रिएक्टिव पावर इंजेक्शन करता है. सो दे शेयर द रिएक्टिव पावर अमंग देमसेल्व्स. सो उससे क्या होता है, D-STATCOM एज वेल एज DVR दोनों की पावर रेटिंग कम हो जाती है. सो द पावर रेटिंग इज ऑफ the D-STATCOM inverter and DVR inverter is smallest in Upqc's. So from the point of view of rating of power, power rating of voltage source inverters, power rating of D-STATCOM and DVR, Upqc's is generally preferred. And then there are many control algorithms, because now when you operate this Upqc, you have to see it's very tough. Earlier you have learned how to operate D-STATCOM alone, and you have studied PQ theory or instantaneous reactive power theory or alpha beta theory, control algorithm for generation of reference, these compensation currents, and for realizing those currents using a D-STATCOM by proper switching of D-STATCOM switches. और DVR में भी आपने control algorithm मैंने आपके साथ discuss किया, how to generate the reference compensation voltages and how to synthesize those voltages using voltage source inverter, that's DVR, by proper switching of the switches, how we can synthesize those voltages. Okay, and there are many control algorithms, both D-STATCOM and DVR, 10 to 12 control algorithms or more than 10 to 12 control algorithms for generation of compensation currents or compensation voltages. It's already reported in the literature. You can go through the literature. But when you have to operate Upqc is a combination. It has both D-STATCOM as well as DVR. and a common DC bus. The control is complex. It's not so easy. The control of Upqc is complex as compared to that of DStatCom alone or DVR alone. Here also, if you go through research literature, many control algorithms have been proposed in the literature for operation of Upqc, for proper operation of DStatCom of Upqc, and for proper operation of DVR part of Upqc. Many control algorithms are already reported in the literature. And I will share one thing with you, that one of my research scholars, Miss Anha Farooq, she is a part-time research scholar. She is working as a junior engineer in power development department, and she is doing PhD under my supervision on part-time basis. She is working on Upqc, and उसने भी अच्छा काम अभी तक रिपोर्ट किया है. And she is developing some control algorithm and some changes in the topology of Upqc, and she is trying to improve the performance of Upqc for addressing both voltage as well as current related power quality problems. So therefore, Upqc for many critical loads like industrial loads, etc., is considered as one of the best solutions because it addresses voltage related as well as current related power quality problems. So therefore, over last 5 lectures, we have discussed, we discussed module number 3, and it took us about 5 lectures to complete module 3. In module 3, we have studied first series compensation or voltage compensation by DVR. We have developed the control algorithm, the basics, the phasor analysis we have done, comprehensive phasor analysis, injection techniques, how to implement the compensation by DVR, and how to implement the compensation technique, and all that we have done that. And in today's class we have covered Upqc part of this module 3 also, unified power quality conditioner. We have studied why do we need Upqc, what is a Upqc, why is it needed, in what situations do we need Upqc, what's its basic structure. I have shown you the schematic diagram and complete circuit diagram also, and we have also studied different types of Upqcs, right shunt Upqc, left shunt Upqc. Right shunt Upqc is preferred over left shunt Upqc because the rating of both DVR and DStatCom is smaller in right shunt Upqc as compared to left shunt Upqc. And then depending upon the power rating or type of injection method of DVR part of Upqc, we have classified Upqcs in 3 types: Upqcq, Upqcp, and Upqc's. We have studied their operation done with the help of phasor analysis. And with the help of phasor analysis, we have found that Upqcq, although it is a capacitor supported Upqc, it does not need any energy source at its DC bus, but although it can do the voltage sag compensation, it fails to do voltage swell compensation. So therefore it is ruled out in most of the applications. Then you have to make a choice between Upqcp and Upqc's. From the point of view, for both the cases you need energy storage at the DC bus, but from the point of view of power rating of voltage source inverters, that is DStatCom and DVR, we generally prefer Upqc's. Okay, we have done the complete phasor analysis of this. With this, I will end my today's lecture, and this marks the end of module 3. Now we are left with last module of your syllabus, module number 4. Hopefully, inshallah, next lecture will start with module number 4, and within 3 to 4 lectures, I will try to finish that module 4, and that will mark the end of the syllabus. With this, I will end my today's lecture. I advise all of you to go through this lecture and other lectures also. And in case of any queries, any doubts, please get connected to me. Wish you all the best. Thank you.